Moving on to the next basic concept of thermochemistry, exothermic versus endothermic reactions. So we have already discussed this briefly when we were introducing the zeroth law and the first law of thermodynamics, basically the first law of thermodynamics. But let's have a quick recap of what exothermic and endothermic means. Exothermic reactions are those reactions in which, so say, let's suppose you have a system which is getting heat inside. So the surrounding is providing the system heat. Okay, so heat is going in. So if the heat is going in, this is called endothermic, because endo means in and therm means heat. So heat is going in. Okay, the opposite is true when heat might be coming out. So if heat is coming out, then this is called exothermic. Why? Exo means heat out. Okay. Now this is a very simple concept. If heat can go in and heat can come out. But how does the sign change in the Q and what is the convention? Like when the convention was Q is a positive quantity if it is going in. Okay, so Q is positive if heat from the outside is going into the system, and Q is negative if heat from the system is coming out. Okay, the similar convention is thereby taken by the delta H, the enthalpy change of the reaction. So all exothermic reactions will have negative values and all endothermic reactions will have positive values. This is a general convention that is being used, okay? Because the heat is going in, it is increasing the heat inside, so it makes more sense to get the Q positive, and since Q is positive, H becomes positive. So because the final state of that system has more heat than the initial state, because the heat has flowed inside the body, therefore the delta H is positive in the case of endothermic, and in the exothermic delta H is negative. So in this case, if you're holding a reaction container in which an exothermic reaction is going on, so you will feel warm. Why? Because the heat is coming out and you are outside that system. If you're holding this block and heat is coming outside from that block into your body, so your body is getting heat now and therefore you will be feeling warm, and the opposite is true for endothermic, in which the heat from your body, from the surrounding, your body, is going into the system. So heat is leaving your body and going into the system. So if you're holding that block and there's an endothermic reaction going on, so you will be feeling cold. Okay. Now, simple concept, it was just a revision of what we learned earlier. Now, let's introduce a new concept called the molar enthalpy of combustion. Okay, what is the molar enthalpy of combustion? So first of all, what is combustion? Combustion is anything that is you're burning, right? So if you're burning something in oxygen, that's called combustion in a very lame manner. What is combustion? Anything that if you're burning. So what do you generally burn? Anything that gives out energy or gives out an exothermic reaction are those things that you generally burn. Like you burn fuels, you burn fossil fuels. Why? Because if you burn them, energy from the system comes out, it's an exothermic reaction and makes you feel warm. So room heaters in the past where we were burning some kind of fuel, so that when you burn those things, heat from inside the body will come out and the room itself will become warmer. So let's take an example. Let's take an example of burning methane. Okay. Actually, people used to burn methane in the past. Okay, so I'll just getting this example. This is being a gas I'm representing in here. So reacting with oxygen is basically burning. If anything reacts in the free presence of oxygen, that is basically burning. Okay, this will give you 2 CO2 plus water, 4 waters, okay? And this is a gas, this is a gas, this is a liquid, okay? Now, the amount of heat exchange in this reaction, so we saw how we can calculate the delta H. What does delta H means? Delta H just means this. If you want to calculate the delta H of that reaction, you just have to use this. So you know the stoichiometric coefficients. Now, if you know the enthalpies of the individual reactants and the products, you can calculate the delta H of that reaction. Now, let's suppose we know each of them, and someone calculated the delta H at 298 Kelvin. Basically, for all our purposes, whenever I write 298 Kelvin, it will be 298.15 Kelvin. But for simplicity's sake, I'm writing here just 298. So for delta H at 298 for this reaction is minus 1780.72. And the unit of delta H is joules, right? So this is kilojoules, okay? Now, this was the enthalpy change for this reaction, okay? Now, if we have to define the molar enthalpy of combustion, what is being combusted? What is being burnt? Methane, right? So if we want to calculate the molar enthalpy of combustion of methane, we have to find out what is the energy change of burning methane, of burning 1 mole of methane. So the delta H value for this reaction, if you have 2 moles, is delta H of minus 1780.72 kilojoules. But if you just have, say, this, okay, just burning 1 mole at 298 is just by 2, which is minus 890.36 kilojoules, okay? This will be the delta H. Now, this was done for just 1 mole of methane, right? So it was per mole. So if you burn just 1 mole of methane, you're getting that. So that delta H that we get by burning 1 mole of any particular compound is the molar enthalpy of combustion of that compound. So this change in delta H is written as the combustion, just C, of the reaction for 1 mole. So this is basically equal to this for this reaction, okay? It is very similar. The definition goes like this. The delta H value for combustion for 1 mole of any combustible material in air or any other gas is, so the delta H for the burning of 1 mole of methane in oxygen is basically the definition of molar enthalpy of combustion. Okay, simple enough. Now we can take a few other examples to show this. Okay, so you can have the burning of ethane. So I'll just write it here. You can have 2C2H6. This is ethane. You burn it in oxygen, you're getting 4 CO2 plus 6 H2O. This is liquid, rest are gases. And the delta H for the reaction at 298 is minus 3.119.6 kilojoule. Now, if we want to find out the delta heat of combustion for methane, how will you do that? For methane, this will become 3.119.6 divided by 2 because there are 2 moles. For burning 2 moles, the delta H was this. For burning 1 mole, the delta H will be this much, okay? Whatever that is. Okay, so pretty simple, huh? Now, you see, whenever we burn, we are getting liquid water, okay? We are getting liquid water. So an experimenter, actually did those experiments in which she burned the methane or ethane or any other combustible material. She burnt it in oxygen, and she kept the relative humidity of the system at 100%. That means whatever whatever H2O was being produced would quickly turn to liquid. So all the H2O that was being produced goes to a liquid form. So the experimenter kept the system at 100% relative humidity, and that is why this H2O is liquid and this is not vapor or any other thing. Like this is not vapor, because at that temperature I'm keeping the relative humidity of the system at 100%. So any H2O that is being produced is quickly going to the liquid state. Okay, so this is basically the molar enthalpy of combustion. Okay, so this was an example of an exothermic process. Why? Because heat was being produced, like heat was being generated by the system. Okay, and this is evident by this negative sign, right? So we saw that whenever you have this negative sign, the things were exothermic. Okay, so you see here, this is negative, right? Even this is negative. So these are some of the examples of some exothermic processes. Okay, now let's see an example of an endothermic process. Okay. Okay, so let's see some examples of endothermic in which you have hydrogen gas plus iodine the delta H of the reaction at 298 is plus 26.50 kilojoule per mole. Okay, so in here you see that this is an endothermic reaction. How do you know that? Because the delta H has a positive sign in here. Okay, now this could also give you, okay, because half of H2 and half of I2 will give HI and not 2HI, right? And that's why you have a per mole. So the delta H of this reaction is basically that. Now this delta H, you see how HI is being formed. Okay, you're producing HI from its constituents. Now this is called the molar enthalpy of formation. So anything when you're forming, so let's define a new concept, new term, the molar enthalpy of formation. So we saw the molar enthalpy of combustion. This is molar enthalpy of formation. Okay, molar enthalpy of formation. Molar for 1 mole, so we are producing 1 mole of HI, and that is why the delta H of this reaction becomes the molar enthalpy of formation of HI. Now, there is this concept in which the for calculating the molar heat of molar enthalpy of formation, this compound, if you're calculating the molar enthalpy of formation of HI, this has to form from its constituting elements, right? So it has to come from the elements that form. Now, in here, I am giving you a reference of a concept called the elemental reference states. We will study about what actually reference states mean, because So just for an example, now I said that HI is being produced by its constituting elements, and those elements are should be in their reference states. Now, say for example, you're forming quartz. Okay, so if you're forming quartz can form from silica crystal, and it can form from oxygen gas, right? So these are the two constituting elements. But the constituting elements themselves can be in different forms. For example, if you are forming iron oxide, some kind of iron oxide, and you want to find out the delta heat of formation of that iron oxide. So what does iron oxide come out from? So it comes from iron and oxygen. So the question here comes, what is the state of that iron? What is the state of the oxygen? Is it oxygen 2 gas, or is it oxygen atom, or is it some other form of oxygen in some different kinds of state? The same goes for iron. Is it oxygen? Is it iron gas, or is it iron liquid, or is it iron solid? If it is solid, then what kind of solid? So these are the questions that will be answered in elemental reference states. So for now, just understand that whenever you have a molar enthalpy of formation, so if you are trying to find out what is the delta H of that reaction that is producing 1 mole of that compound from its constituting elements, and those constituting elements should be in their reference state. So we'll deal with that. Okay, so the molar enthalpy of formation is defined as the delta H of the reaction for the formation of 1 mole of a compound from its constituting elements. Okay, so this is a pretty simple concept, like similar to what we saw for the molar enthalpy of the combustion. So similar to that, this is molar enthalpy of formation for 1 mole of any compound. Okay, now there are some other delta H values with a similar concept. So you see how we are trying to calculate the delta H of a reaction, and then for a particular type of reaction, we are giving a particular name. So this in here, the type of reaction that was going on was combustion. So for this reaction was a combustion reaction, right? So for a combustion reaction, the enthalpy change became the molar enthalpy of combustion. This was a formation reaction. So something was forming out of its constituent elements, like hydrogen, iodine were the constituent elements of HI, and HI was being formed. So when you're forming something, the delta H becomes a molar enthalpy of formation. Similar to this concept, let's assume that you have, so we can define the molar enthalpy of any reaction with this, right? So we can have any reaction, and that reaction will have a molar enthalpy of the reaction, right? Of any reaction. Let's say, for example, you have a equation like NH3 gas plus H2S hydrogen sulfide gas is giving you NH4SH in the solid state. The delta H, the delta H of this equation at 298 is minus 90.32 kilojoules. Okay, so this is a general reaction, right? Any two reactants are producing this reaction. So there is an enthalpy change associated with this reaction. So the enthalpy change associated with this reaction is basically being called the molar enthalpy of that reaction. So this was the formation type, so we gave a special name, so molar enthalpy of formation. We gave a special name to the combustion, and here is just a reaction, and we are just telling, okay, if we have this kind of reaction, we'll call the molar enthalpy of that reaction, right? So any reaction, so it could be any reaction. So let's give it a sign like we gave the sign for the others. So F was for formation, R is for reaction. So this is basically this, okay? Now this could be, you can have different kinds of reactions in here. So I have calcium carbonate could be dissociating into CO2 and CaO, right? So that could be a reaction, and if you have a delta H for that reaction, that delta H becomes the molar enthalpy of that reaction. Like when you have like 1 mole of the things getting produced, like 1 mole of that things are, so it becomes a molar. So a molar concept when you have everything in per mole basis. Okay. Now similar to this, you have molar enthalpy of hydrogenation. Like it's nothing special there. Like if you have a reaction in which you are hydrogenizing something. So for example, if you have now, what is hydrogenation? Hydrogenation is the addition of hydrogen. So when you have a compound, if you add one molecule of hydrogen to any compound, that becomes hydrogenation. Okay, so this is very common in organic chemistry, in which say you have a compound, an alkene, right, with an unsaturated bond in it. So this is in the gaseous phase. We have hydrogen in the gaseous phase. This gives rise to C4H10, which is again in the gaseous state. The delta H of the reaction at 355 Kelvin is given as 126.95 kilojoules per mole. So this is 1 butene, something like this, and this is becoming this. So you are going from 1 butene you're adding hydrogen, you're becoming butane. Addition of hydrogen. So addition of hydrogen is a hydrogenation reaction. So similar to the concept in earlier, the delta H of the reaction will now be called the molar enthalpy of hydrogenation, right? So what is the molar enthalpy of hydrogenation of butene, of 1 butene? When you have this 1 butene reacting with hydrogen, the delta H of that reaction becomes the molar enthalpy of hydrogenation. Very simple concept. It's just a reaction. We just gave it a different name because there is a hydrogenation going on. So what if now you have isomerization going on, okay? You might have heard about isomers. When different isomers change into interchange, the delta H of the reaction in that interchange is basically the molar enthalpy of isomerization. Very simple. So let's take an example of, say, you have cis-2-butene, okay? This is isomerizing into, just use an equal to sign, into a trans 2-butene, and there is an associated delta H. I don't have the number in here, but let's suppose that that delta H, so that enthalpy change of this reaction will be called the molar enthalpy of isomerization, because the reaction is basically an isomerization reaction. Okay. Similarly, you can have molar enthalpies of fusion, like say you have ice, you have water ice, and that ice is melting to form water, liquid water. So there is an enthalpy. So if you have H2O ice and you are forming H2O liquid, now there is a delta H associated with that. Now, if I ask you to guess what can be the delta H of that, will it be exothermic or endothermic? So when you hold ice and when it's melting, will this is this an exothermic process or an endothermic process? Let's try to figure out what this is. The ice is taking heat from the outside in, and then it is giving you H2L. So since it is taking heat in, this is an endothermic process, and this will be greater than 0. So the delta H of this reaction will become the molar enthalpy of melting or fusion, right? Pretty simple concept. Now, you can have molar enthalpy of sublimation when you have a solid turning into a gas. You can have molar enthalpy of vaporization when you have liquid turning into vapor state. So all these kind of things are there. So you can have molar enthalpy of melting, vaporization, and sublimation, and all three will be endothermic because all these are requiring energy. All these are going from a low energy state to a high energy state, and in order to do that it requires energy. So this is basically an endothermic process. Now we'll be dealing with some kind of transition. So like suppose you have some, this is a type of transition, but there could be other transitions in which the process is not endothermic, the process is exothermic. Heat is being released when that is happening. So all these kind of like transition in their phases also have fixed terminologies, like the molar enthalpy of transitions. Now we will deal more about these transitions in a subsequent lecture when we'll be discussing about the concept of the second law of thermodynamics with entropies and things like that. So the molar enthalpies of transition will be dealt in greater detail there. But I hope you understand that every reaction has a delta H associated with it. So you can call that the molar enthalpy of the reaction, but if that reaction has a particular name associated with it, so if that is a combustion or a hydrogenation or an isomerization or a phase transition or fusion or melting, whatever, that delta H takes a different name because it's a different equation. We have a special name for that equation, and that is why the delta H gets a different name associated with that. It's as simple as that.